there, students. So welcome back. And in today's lecture, we are going to continue in this current chapter talking about ionic and molecular bonding. In the previous lecture, we focused a lot on ionic compound, and in today's lecture, we're going to focus on the other half, which is on molecular compounds. To connect back to our previous lecture, remember that the driving force behind bonding in molecules is that atoms need to fulfill a rule called the octet rule, which means they must have 8 electrons on their valence shell, or the duet rule for hydrogen and helium, meaning they have 2 electrons on their valence shell. And remember that the reason for this is that atoms will always want to have the same valence electron configuration as that of the nearest noble gas, because every noble gas will have a full shell of electrons, which gives it a special stabilization that all atoms want. And so if you are not a noble gas atom with that full shell of electrons, you must interact with other atoms, resulting in what is called as a bond. In the previous case, we saw that you can achieve this by giving and taking electrons, resulting in something called an ionic compound, where the atoms are attracted to each other by an ionic bond. And this occurs when you have a metal and a nonmetal. A metal is an atom that likes to give away its electron, whereas a nonmetal is an atom that likes to take away electrons from others. So it's a perfect pair. What happens though if you have 2 nonmetals together? For example, if you have 2 chlorine atoms, both of them will have 7 valence electrons only, and both of them will need 1 more. So chlorine is not going to take 1 electron from the other chlorine and making itself happy, while the other chlorine is now 2 away from a full valence electrons, right? But what you can do is share electrons to make a bond, what is known as a covalent bond. And this is what we will focus on today's lecture. Here are some more examples. Let's say you have 2 hydrogen atoms, and as you know, hydrogen is element number 1, so it has 1 electron. It needs 2 electrons to fulfill its first shell of electrons. So if you are a non-metal like hydrogen and there are no metals around to give you that full shell of electrons, so you come together closer and closer, putting those electrons that each of you have in between you two. They are being shared by both hydrogens. So from the perspective of the left hydrogen, he would see that he has 2 electrons, a full shell of electrons. And from the perspective of the right side hydrogen, he also sees that he has 2 hydrogens, a full shell of electrons. And because of this, this molecule is more stable than the 2 hydrogens independent of each other. And because it is more stable, they prefer this state and they form a bond. We can signify the bond between the hydrogens with those 2 electrons represented with a line in this Lewis structure drawing. And in fact, this sharing of electrons occurs with many other combinations of nonmetals. For example, here, if you have again a hydrogen, it needs 1 more electron to fulfill its duet rule. And you have chlorine, which has 7 electrons, so it needs 1 more electron to fulfill its octet rule. So what happens is, again, there will be no giving or taking in this case, but there will be a sharing of electrons, with 1 electron coming from hydrogen and 1 electron coming from chlorine. Again, in this arrangement, you can see the hydrogen has 2 valence electrons, and at the same time, chlorine has 8 valence electrons, duet and octet. Again, we can represent this bonding with a line that connects hydrogen with chlorine. These are 2 examples of what we call Lewis structures. And in a Lewis structure, we only care about valence electrons. Notice that chlorine has 17 electrons, but we don't draw all 17. We only depict the valence electrons in chlorine. In Lewis structures, a single line represents a pair of bonding electrons, whereas 2 dots represents a pair of non-bonding electrons. So for example, in this case, chlorine has 1, 2, 3, 4, 5, 6 electrons are not involved in the bonding. You can consider these electrons solely belonging to chlorine, whereas that line between hydrogen and chlorine represents a pair of 2 electrons that are shared between hydrogen and chlorine. Let's have some more practice with drawing Lewis dot structures of molecular compounds. From a conceptual perspective, you can draw these 2 atoms of fluorine separately with their valence shell of electrons. Remember, fluorine belongs in group 7A, so it has 7 valence electrons. So you can depict those 7 valence electrons as dots around fluorine. And you can also imagine that each fluorine will have 1 electron that will be shared between the 2 of them. Each fluorine will contribute one electron in that bonding pair. And you can depict that pair of bonding electron right in between the two atoms. Again, we call that pair of electron a bonding pair, and the other pairs are called the lone pairs. They are not involved in bonding. And again, a pair of electron means two electrons. And to simplify this structure, every time you have a bonding pair of electron, we want to draw a line that connects the two atoms. So we use this Lewis structure to represent this molecule of fluorine. Let's try another example. This is CH4. It is known commonly as methane. It is a molecular compound that is composed of a carbon and 4 hydrogens. The Lewis dot structure of carbon has 4 electrons around it because carbon is in group 4a, whereas hydrogen has 1 electron because it is in group 1a. From this, we can see that carbon needs 4 more electrons to be an octet, while hydrogen needs 1 more electron to be a duet. So for this bonding to occur, each of the hydrogen will make a bond with the carbon. So carbon will make 4 bonds. As seen from this depiction, you can see that there are 8 electrons surrounding carbon, and you can see that for every hydrogen, it is close to 2 electrons. So every atom in this molecule is happy with an octet or a duet. Again, those bonding pairs of electron can be depicted with a line connecting the atoms from which the electrons are being shared. So in this slide, I was trying to give you a conceptual understanding how bonding occurs in molecular compounds. Now, Lewis structures can get very complicated, so we will need a more systematic way in drawing them. In drawing any Lewis structures, you can follow these 4 steps. First, you have to determine the arrangement of the atoms, how they are connected to each other. Then you need to determine what is the total number of valence electrons contributing from those atoms, making sure that you do not have more or less valence electrons than you started out with from the individual atoms. Then the next step involves bonding the atoms together, and in this step you have to figure out what is the central atom. And lastly, in step 4, you put the remaining electrons around each atom, making sure each will have an octet. And if an octet is not achieved, you might have to make the lone pairs become bonding pairs, and resulting in something called double or triple bonds. Let's see how you can use this guideline to help you draw the Lewis structure for carbon dioxide, CO2. Again, step 1 says to determine the arrangement of the atoms. And most of the time, this simply means which atom is your central atom, the atom that the other atoms are connected to. There are 2 things you can use to determine what is your central atom. The first is symmetry. So for example, in this case, you have 1 carbon and 2 oxygens. How would you arrange this molecule to provide symmetry? Would you put the carbon in the middle, flanking it with 2 oxygens on the outside, or 1 oxygen in the middle, flanking on one side carbon and one side oxygen? You would put the carbon in the middle because that will give you a symmetry within this molecule. Another guideline that could help you to determine this is that you want to put the least electronegative atom in the center. This idea of electronegativity will be covered in the second part of this lecture, so for now, let me tell you that carbon is the least electronegative atom between carbon and oxygen. Once you have determined the connectivity of the atoms, in step 2, you need to count the total valence electrons. You say to yourself, I have a carbon. Carbon belongs to group 4a, which means it has 4 valence electrons. So if I have only 1 carbon contributing 4 electrons each, that gives me 4 electrons. Then you move on to the next atom. You say to yourself, I have oxygen. Oxygen is from group 6a, so it has 6 valence electrons. I have 2 oxygens, so 2 times 6 is 12. So from the oxygens, I have 12 electrons. That's all the element I have, so I add them to give me a total of 16 valence electrons. This is the number of valence electrons you should always make sure you have at the end. You do not want to have more or less than this. Okay, step 3. Step 3 says to connect the atoms together. Remember that we have already determined that the connection is going to be oxygen to carbon to oxygen. So now we just have to connect them. And remember that this line just means that there are electrons being shared between those 2 atoms. Step 4. Step 4 is the most challenging step, and it might require the most work. Step 4 says you have to place the remaining electrons around the atoms to complete the octet. It is best to start putting electrons around the non-central atom. So in this case, the central atom is carbon. So I would start putting electrons around the oxygen. Remember from step 2 how many electrons we have. We have 16 electrons, and we have already used 4 electrons. Right? 2, 4. So this is our 6, 8, 10, 12, 14, 16. Voila! We have used all of our valence electrons. So now we need to make sure that each atom has a full octet. Counting electrons around oxygen, we see that each oxygen has 8 valence electrons, whereas that carbon has only 4 electrons. 2 electrons here and 2 electrons here, making that 4 electrons around carbon. So carbon does not have an octet. So I like to say that this structure is not happy. And since carbon does not have a full octet, he would like to share electrons to achieve that full octet. And so carbon will look to his neighbors and ask to share electrons. And remember that when electrons are being shared, they are not taken. So for example, if I share this pair of electrons between this oxygen and this carbon, oxygen will still have its 8 valence electrons. And it doesn't matter which pair of electron you take, it's just a representation. After we do that, we can see that now carbon is getting happier. It has 6 valence electrons, but not yet 8 electrons. So you can continue to share further. And for the sake of symmetry, I'm not going to ask this pair of electrons to move in from the same oxygen again. I'm going to look to the other side, since we haven't shared anything from this oxygen. We can now ask this oxygen to donate its pair of electron in. So when that oxygen donates its electron in, that carbon now will have a full octet. When each atom has a full octet, you know that you have your complete Lewis structure. This kind of looks messy, so at this point we would want to redraw our Lewis structure. Every bonding electron should be represented with a line. So in this case, since there are 4 electrons or 2 pairs of bonding electrons between the oxygen and the carbon, we can draw it as 2 lines instead. That is called a double bond. Let's do another example with hydrocyanic acid, or HCN. Again, first step is to consider what is the center atom. For sure, hydrogen will not be your center atom because hydrogen can only make 1 bond. If you can only make 1 bond, you can't be the center atom because a central atom will have to make bonds with all the other atoms. So now you're left with either deciding carbon is the center or nitrogen is in the center. So if you know that carbon is less electronegative than nitrogen, then you will be able to decide that carbon will be your central atom. Like I said, I will have to give this to you since we haven't learned about electronegativity. Step 2. Let's count how many valence electrons you have from this molecule. Hydrogen will give you 1, carbon will give you 4, and nitrogen will give you 5, giving you a total of 10 valence electrons. Connecting the atoms that we know with a bond, we see that we have used up 4 of our valence electrons. We only have 6 valence electrons left. And the next step, step 4, is to put in the rest of the electrons first around the outside atoms. In this case, that's nitrogen. So we put 2, 4, 6, giving us a total of 10 electrons. So we have used all of our valence electrons. Do we have a full octet for everybody? So hydrogen's happy, it has a duet. Nitrogen is happy, it has 8 electrons. But carbon, again, has only 4 electrons. Again, carbon needs to share electrons, so it looks around its neighbor and see where electrons can be shared. Hydrogen has no more electrons to share, so your only option is to share electrons from nitrogen. How many electrons for nitrogen would you need to be happy? You would need 4 more electrons, because you only have 4 electrons as it is right now. So to do that, we move 2 additional pair of electrons to be between carbon and nitrogen. Hydrogen still has 2 electrons, so duet is good. Carbon has 1, 2, 3, 4, 5, 6, 7, 8. It has 8 electrons, so it has an octet. Nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. Also an octet, so everybody's happy. Again, there are 6 electrons between carbon and nitrogen, or 3 pairs of bonding electrons between carbon and nitrogen. So we can represent those 3 pairs of bonding electron again as lines, this time 3 lines representing a triple bond. So now you are exposed to single bonds, double bonds, and triple bonds. Those are the 3 types of bonds you will see in this class. Notice in this case how many bonds are connected to carbon. 1, 2, 3, 4 total. In this case, how many bonds connected to carbon? 1, 2, 3, 4. In this case, how many bonds connected to carbon? 1, 2, 3, 4. That is not a coincidence. Since carbon is in group 4A, has 4 valence electrons, so it needs 4 more electrons to fulfill its octet. In order to fulfill its octet, it needs to share 4 electrons from others, so it will form 4 bonds. This is a pattern you will see in covalent bonding. Silicon below carbon is also in group 4A, so it will also have 4 bonds. Nitrogen, as in the previous example that we just saw, has 1, 2, 3 bonds. Nitrogen will always have 3 bonds. Again, because it is in group 5A, it has 5 valence electrons, so it needs 3 more electrons to be an octet. In order to obtain those 3 electrons, it will have to share, making 3 bonds. Phosphorus in the same group will also make 3 bonds. Whereas you move to 6A groups, oxygen and sulfur, they will always make 2 bonds. Moving on to the halogens, 7A group, they will always make 1 bond. The same is true for hydrogen, which needs that duet, so it will need 1 more electron, making 1 bond. Now here's an exception. Boron in group 3A will always make 3 bonds. Now 3 times 2 electrons each in those bonds give you 6 electrons. So it turns out there are some elements that does not have to follow the octet rule all the time. So boron will have 6 valence electrons and it will be happy. And there are actually other elements that will have more than 8 electrons and it will be happy too. And the reason for that exception is beyond the scope of this class. So in this class, we just need to follow that every atom will either follow the duet or the octet rule. And when they follow those rules, you can always count on carbon having 4 bonds, nitrogen having 3 bonds, oxygen having 2 bonds, halogens having 1 bond, so on and so forth. So that's how you draw Lewis structures to represent the bonding in molecular compounds. Probably will need a lot of work to get the hang of this, and we will do a lot of practice in class.